Okay, so we are going to talk about our Explorer for today. 17.2, or really just dealing more with logarithms here. It says, how long will it take? So a colony of 1,000 bacteria doubles in population every hour. Explain why we can write h equals log base 2 of x to represent the number of hours h it takes for the 1,000 bacteria to reach a population of x thousandths. So what we want to do is we want to explain why we can write it like log base 2 of x to represent the number of hours h it takes, right? H being the hours, to be 1,000. So what we know from before in this top function is that we have an exponential, which is 1,000, because that's what we start with. And then that's times 2 to the power of x. So 1,000 times 2 to the power of x. So why can we write it as log base 2 of x equals h? Well, what we're going to do if we put a y here is we can go through and find out what around the world might do here, right? If we're looking at, let's see, for 1,000 bacteria to reach a population. So if we do around the world, say we kind of get rid of this 1,000 and we're just going to assume that it is equal to 1,000th. So we divide both sides and we get 2x equals y over 1,000. And the reason, again, that we did that is because in the problem it says it takes for 1,000 bacteria to reach a population of x thousand. So by dividing by that 1,000, now we're assuming that y is going to be in thousands. So if we then do around the world, now we can write it as log base 2 of y, or x, depending on, we're kind of flipping these around. So I'll put this y over 1,000 so we can match it up, and that will equal x. So x is normally time, and it is in this problem, right? Doubling every hour, h being hours. Y over 1,000 would then translate to this x. Why? Because it's 1,000 bacteria to reach a population of x thousandths. So y over 1,000, we would need to get that 1,000 in there in order to find it. I know, very complicated, but that could be explained why, just solving it through. Question number 2 here says, complete the table with the corresponding values of h. So using the table, going back to this function, h of x, or excuse me, h equals log base 2 of x, complete the table. So if I plug a 1 in here for x, right? So that's log 2 of 1. What power, that's what log means, what power on 2 do I need to get 1? Well, we know the only way we can take something to a power and get 1 is if that value is 0. So h would be 0. What power on 2 would I need to get 2? A power of 1. What power on 2 would I need to get 4? A power of 2. Now, if you want, we can always go back and we can take this to Desmos. Brain fart there. When I go to Desmos, I'll hit graphing calculator. Let me bring it back over here to this. And what we'll do is we'll create a table. So we know that the function is log base 2. I don't know why it's not going to let me put the 2 there. I guess the only way to do that is to bring this up and click this log base A. And then we put an X here. Or we could say table. Remember, we did this yesterday, or the other day, depending on when you're watching this. And this will just type out what our X values are in this table. So 1, 2, 4, 8, 16, 50, 80. So 1, 2, 4, 8, 16, I remember 50 and 80. So 50 here and an 80 here. And then for y, what we can do is we can replace this y with our log base 2 of, and now we'll say x1 because that's where we get this information from. So when we do that, this is our table that we can fill in. And so what you'll do is you can pause this and you can take these numbers and put them in here, right? So we know that this one would be the 4. Forget how I get those um, tools back, but it's okay. This one will be the 4, and this one will be that, excuse me, the 3, and then the 4, and then the 5.64, and then the 6.32 that you can plug in down here. All right. Let's move on here, and it says plot the points, the pairs of values in the coordinate plane, make 2 observations about the graph. So here it is. They've got it out for you. What I recommend you do is just take it and plot it, right? And then make a couple observations about this graph. So here it is. It nowhere does this say to connect the dots. So you are not asked to connect the dots. So we know we can put at 0, we're up here at 1. However, this is spaced 1, 2, 3, 4, 5, so perfectly spaced there. So 0 at 1, I'm sorry, at 1, you would go to 0. At 2, you'd go to 1. At 4, wherever your 4 is, then you come up here to 2. At 8, you come up to 3. At 16, you come up here to 4, and then so on and so forth. So one observation that I would make as I'm looking at this is it kind of looks like a square root function. The square root of x looks very similar to that. Not quite there, and I could maneuver this around to get there to make it look like that. Like I could shift it over to the right one. Now it looks pretty similar to that, right? So one observation is it looks very similar to a square root function. Another observation can really be anything that you notice. It looks like it's going to increase at a much slower rate as the values of x increase at a higher rate. So the y's are increasing slower as the x are increasing higher, which is kind of like that square root function. Those are just 2 things you can observe about that. Coming down to question 4, it says use the graph to estimate the missing values in the table. So if I come back over here and maybe I decide I want to connect all these, as you can see, I connected the dots. Using Desmos, you just hold that until it pops up. You can make it a dotted line. You can make it, a different color, whatever you want, or red. So I don't know if that's red or not. Probably this one. And so now what you're going to do is you're going to estimate. So at 10, what do you think this is at 10? Well, here's 10. There's 5. It looks like it's going to be between 3 and 4, maybe 3.2. So you put a 3.2 in there, right? 3.2. For 24, it looks like over here 24 on my graph. Come up here between there's 5 up here, really close to 5. How about 5.5, 5.55, whatever. Then the next one's 72. So on your Desmos, just keep on scrolling down, right? 72. Here's 72. Right here, come up. Well, at 80, it's 6.3. So at 72, it's probably going to be a little bit less than that. So why don't we call that a 6.1? And so then you can make those estimates in that table. All at once there is an estimate, okay? So 17.3 says another logarithmic function. So we've done 17.2. Let's look at 17.3. Earlier we saw that h equals log 2 of x, what we literally just did, represents the number of hours 1,000th bacteria doubling every hour to reach a population of x in thousandths. So suppose the function is defined by log base 10 of x, represents the number of days it takes 1,000 of another species of bacteria to reach a population of x in thousands. How is this population of bacteria growing? So before we saw it was doubling. and the doubling was down here underneath. So if now we have a 10 as the base, how is this population growing? In this case, we would say that the population is multiplying by 10. Okay, population is multiplying by 10 every day. Not in hours, right? Number of hours, number of days. Doubling every hour. This one is multiplying by 10 every hour. Use graph D, use graph function D using graphing technology and make two observations about the graph. Hey, graphing technology, here we are. So we know that log base 10, we don't have to actually put a base 10 there, of x is here. So let's make some observations about this graph. Oh, let me get rid of this other one. So we can just tap that and make it go away. When we do that and we're looking, we can see a couple of things. One, I see, x is 1, y is 0. So on the first day, the population is 0, right, of bacteria. So on day 2, the population of bacteria is 0.301, or, right, we would multiply that by 100 to get that. But it looks like it's increasing really quickly at first and then slows down. Really quickly at first, slows down, but we never have 0 bacteria. And you can highlight that key point there if you'd like. But again, what does X and Y represent? So if I was to take this point to 0.31, so to 0.31. If I'm going to take this function and think about it as it relates to this problem, X, right, in thousands. So 1,000 of a species, the bacteria to reach a population of X, right? It's the number of days. So it takes 0.31 days to reach 2,000 bacteria population. All I got that was from this problem up here. From the information, from the words is where I got that information. That's one observation. The other one is increasing really quickly at first and then tapers off after that, after it hits a certain point. Number 3, use your graph to estimate the values of D50 or day, right? How many days does it take to get 50,000 bacteria, or how many days does it take to get 20,000? And adjust your graphing window as needed. Explain what this means in this situation. So coming back here, if I adjust my window, there's 2 ways I can do this. I can come to the wrench, and the first one I believe was at 50, right? So we actually don't have to adjust the wrench here. We can just scroll over until we get to 50 and then click, and we see at 50, we're at 1.69, 1.699. Okay, so at 50, we're at 1.699. At 20,000, so this is where I'll click the wrench and I'll come down here and I want my last part here to go to 1,2,3,000. Now look how far over I am. There's my 20,000, and I can just click and highlight. 20,000 is at 4.301. So this is at 4.301. Go back and review that if you need help on how to adjust that window. So what does this mean in the context of the problem? Well, the y value is how long it takes to get the x value. So it takes 1.699 days to get 50,000 bacteria. It takes 4.301 days to get 20,000 bacteria. Estimate or find the population after 5 days. So you can do either. You can estimate or you can find it. The way that we would find this is we would plug it back into the function. 5 equals log base 10 of x. So this goes back to around the world. So really, this is 10 to the 5th equals x. And 10 to the 5th just means that there's 5 zeros there. You can also come back and plug it in on the side. If you really don't trust me, 10 to the 5th is going to be 100,000. So after 5 days, there's going to be a population of 100,000. All right, let me clear this. Pause it if you need it. Are you ready for more? And there's 2 questions underneath here for you to look at it. So without graphing, how do you think that the graphs of the equations y equals log base 2 of x and y equals log base 10 of x compare? Do they ever meet? So without graphing, thinking about going back up here, comparing what you found, are they ever going to cross? Are they ever going to meet? Right? And how do they compare? Well, one seems like it's kind of increasing by 2 times, doubling, while the other one's x values are really increasing by 10 times before we actually get to where we're looking. So I'm going to cheat here. I'm going to cheat. And I'm going to do the log base. Let me go back and let's see if I can reset this. It's okay if I can't. No big deal. There's log base 10 of x. And let me come back up here because I do believe I had log base 2 of x. So here they are. Here are the two. There's log base 2 of x, and then here is log base 10 of x. Do they ever meet? Well, you might say they meet at 0. But if I was to come back here and I was to plug in a 0, it doesn't exist. So in actuality, they never really meet. And you can keep scrolling in, but the more you scroll in, the further away it gets, even though it looks like they're going to touch. Right? And I can come all the way down here to where it looks like they're the same thing. But the further I zoom in, the further away they get. They actually never touch. So without comparing, how did the think the graphs exist? It looks like this one's increasing graphically at a quicker rate, but that's just because the x is increasing at a lower rate. Do they ever meet? No, they don't. So then graph both of these to test your conjectures, which we just did. Okay, they're both here. I'll zoom out enough for us to see that graphically. There you go. And it looks like on yours, it's increasing up and down a little bit at a different rate than what mine was. But that's just my maybe if I just made this a 10, or actually, what's the scale that I have here? 0 to 5 for the x. So 0, 5 for the x. What's my scale for the y? I believe it is -3 to 3. Uh-oh. Did they ever cross? Well, before it looked like it didn't, but now that I've done it this way, they do look like they cross. They look like they cross there at 0, 1. Interesting. It's all about the window that you use. Very, very interesting. Okay, there you go. There's all your notes. Have it scanned in. Look at all the different ways that you can submit it. Good luck. Submit it. Get 100.